Hello, and thank you for joining me again. We're continuing our adventure into Riemann sums and integration. Last class, we learned about Riemann sums, and I alluded to the fact that although we can use rectangles to help us estimate the area under the curve, a finite number of rectangles doesn't always work. We need an infinite amount of rectangles. And to use an infinite number of rectangles, we involved limits. So let's continue with this adventure. We're going to be talking about summation notation, and that gives us a compact way to write Riemann sums into a single expression. This lesson will lay the foundation for the definition of the definite integral. This is summation notation. It's a method for summing up a finite number of terms in a sequence. So let's break this down a little bit. So our summation sign is this guy in the middle here. On the bottom, the letter is the index of summation. The number that goes with it is our starting point. On top is our ending point. And then the expression is like the body of our whole system here. So to evaluate a summation, you figure out where you're starting and where you're ending. So we're starting at k equals 1, and we're going to have 1, 2, 3, and 4. We're ending at 4. And each of these values is going to just get plugged in to the expression. So 3 times 1 minus 2, then 3 times 2 minus 2. And because this is a summation, we're adding, plus 3 times 3 minus 2, plus 3 times 4 minus 2. Working all that out, we get a total of 22. So this expression equals 22. So now we're going to take this graph, we're going to create some Riemann rectangles and put that into a summation notation. More specifically, our goal is to find a general expression for the area of the kth rectangle and use summation to add all k rectangles together. We're going to start by drawing rectangles for a right-hand sum with equal subdivisions. We want 6 rectangles going from 1 to 4. All right, so 6 rectangles starting at 1, a equals 1, ending at 4, b equals 4. Now, how wide should each rectangle be? That's this delta x. And we find that by taking b minus a and dividing it by n. So 4 minus 1, we're covering a space of 3 with 6 subdivisions. So the base is going to be 1/2. That's our delta x. There's the first one, second one, 3. All right. Part B, find the height of the kth rectangle whose right endpoint is at x sub k. What does that mean? All right, so look over here. X sub k is our far right point. And we find x sub k by our starting point plus our delta x times what triangle we're on. Okay, so starting point, width of each rectangle, and whichever rectangle we're on. So for our function here, we started at 1. Each rectangle is 0.5 wide, and then k would tell us whichever rectangle we're on. Now the height of the function is going to be f of x, or in our case, f of x sub k. Our function is the square root of x, okay? So the height is going to be the square root of 1 plus 0.5k. Now to find the area of each rectangle, It's just base times height, or width times height. So delta x is the width, and f of x sub k is the height. So for us, the area of each rectangle is 0.5 times the square root of 1 plus 0.5k. So what is this telling me? If I wanted to find the area of the second rectangle, I would figure out 0.5 times the square root of 1 plus 0.5 times 2. And that would be the area of my second rectangle. Now I want all the rectangles added together, so that's where summation notation comes in. I want to add them all together, starting with rectangle 1, going to rectangle 6, using my formula width times height. That seems like a lot, so here's a quick summation of what we just did. Find the width of each rectangle, so that's b minus a over n, that's your delta x. Find the right end point of each rectangle, so that's your starting point, plus the width of each rectangle times k. The area of the kth rectangle is width times height, delta x times f of x sub k, and then you can write the sum. We did a right Riemann sum, and in that case, the k values go from 1 to n, however many rectangles you have. That's what n is. If you do a left Riemann sum, it's just kind of starting from the other side. So you start at 0 and go to n minus 1. But the expressions are the same. Which of the following is the expression that represents the approximation shown below for the graph of 2 over x plus 3? Well, let's go through our process. Delta x is the ending point minus the starting point, divided by how many rectangles there are. 1, 2, 3, 4, 5, 6. So our delta x is 1/2. Now our x sub k is starting point plus delta x times k. So plugging that into the function, my f of x sub k is 2 over, and instead of writing x, I have x sub k plus 3. That's the height of each rectangle. To find the area, I need to multiply by the width, which is 1/2. Okay, so which of these expressions on the left is going to work for us? Not the first one, it's missing the 1/2. Second one is also missing the 1/2. D, I don't know why it goes from 0.5, but that would be what? Starting at half a rectangle? No, we do full rectangles. So rectangles 1 to 6 with our expression. The answer is C. A definite integral represents the area under a curve of a function, and a Riemann sum gives us an approximation of that area. We can't take a Riemann sum with infinite rectangles, n equals infinity, because infinity isn't a real number. However, if R of n represents a right Riemann sum approximation with n subdivision, we can use limits when we want to take something to infinity. Then the exact value of the definite integral can be shown to be, okay, so the limit as n approaches infinity, and now we have this Riemann summation that we just came up with. We also write that in calculus as this definite integral. We're going to break that down. So here we have the graph of the function 1/2 x squared plus 1 from 0 to 4, and the definite integral notation. So we're going to write the area as a right Riemann sum with 8 equal subdivisions. We're going to turn this expression into a Riemann sum. First, what's our delta x? We're ending at 4, starting at 0. We have 8 subdivisions, so our delta x is 1/2. Again, it's not always 1/2. Our x sub k is our starting point, which is 0, plus delta x times k. And we don't really care about that 0 plus. So x sub k is 0.5 k. That's going to get plugged in for this x right here. And then delta x is our dx. Delta x is what goes in this dx right here. So what do we have here? The right-hand sum starts at 1. 8 is the number of subdivisions or rectangles. This guy here is the height, that's the expression of the function. And then 0.5 is the width for the delta x. All right, let's give this a go again. So we're moving from a definite integral to a Riemann sum. You can look down here for some hints if you'd like. First, we figure out our starting point is 2, so a equals 2. Our ending point is 4, which means our delta x is 4 minus 2 over n. We don't have a specified number of rectangles. We want that number to go to infinity. So our delta x is 2 over n. What's our x sub k? Our starting point, which is 2, plus our delta x times k. All right, now this, we're going to plug in to our x value, but we start with limit notation. So as n approaches infinity, we're summing up the first rectangle all the way to the infinitieth rectangle, and we're finding the area, which is the height. So 3 times, here's our x sub k minus 1, right there, and then times our width, which is our delta x. All right, let's try another one. Starting point is -2. Ending point is 0. So our delta x is b minus a, 0 minus -2 over n, which is 2 over n, again. Our x sub k would be starting point plus delta x k. So -2 plus 2 over n times k. And now we throw that all into our lovely limit notation summation. So here's our limit. Limit as n approaches infinity, the first rectangle to the nth. And then here's our height, where x sub k got put in for the x, plus 3 squared times delta x. Okay, one more like this. 0 to pi, starting point is 0, ending point is pi. Delta x is pi over n. X sub k is going to be 0 plus pi over n times k, or just pi k over n. And then plug it all in. And you can kind of see it here. Sine x delta x. Now let's go the other direction, all right? First of all, let's figure out what our pieces and parts are. This 5 over n is the delta x. And in the parentheses here is my a plus delta x k. A is the -2. So we'll start by writing that down. How do we find b? Well, the key to that is right here. Delta x equals b minus a divided by n, which means that 5 is b minus a. Well, we know what a is. A is -2. So b minus -2 equals 5. So b equals 3. Now what's in the parentheses here, that's going to just turn into our x. So here we have our starting point of a, which is -2, our ending point of b, which is 3, and then 5x minus 1 dx, or delta x. Let's put another one of those together. So there's my delta x, my a plus delta xk is in the parentheses there, which means my a is -2. To find b, I've got b minus a equals 2. So b equals 0. So we're going from -2 to 0, 3x plus 4 delta x. This one looks a little bit scary. My delta x is in the same spot. My a plus delta xk is still within these parentheses, but my a is just 0, which means my b, oh, now look at this. We've got a pi over 6 right there. B minus a is pi over 6. A is 0, so b is just pi over 6. And there we have it, 0 to pi over 6 cosine x dx. There's a lot of moving pieces to this lesson. So as you're practicing, slow down and maybe have your notes in front of you. Maybe even watch the video one more time. Wishing you all the best, and I'll see you next time.